New vehicles are heavy because electric vehicles use batteries and they're a lot less energy dense than liquid fuels. And this is a growing problem, especially compounded with stiffening safety restrictions on vehicles. Of course, we can reduce the weight of our vehicles by using composite materials such as carbon or glass fiber. Unfortunately, they are energy intensive to produce and very expensive. Hence, you really only see them in supercars or high performance vehicles. Nature provides us a solution in the form of cellulose nanofibrils. If you've seen paper and you imagine them as fibers, well, these fibers are made of even smaller fibers called cellulose nanofibrils. These have very low density, very high stiffness, and as a result, they perform close to glass fibers with much, much less weight. Unfortunately, as with most natural materials, they do absorb water, they're hydrophilic. And we all know that oil and water do not mix. Composites are based on polymer resins, and these are oil-based. So even if you try to mix these cellulose nanofibrils into plastic resins, they simply won't work. The fibers will just pull out, and the resulting material is very weak. Here's where my research comes in. I'm using another forest byproduct called tannic acid to coat the surface of these cellulose nanofibrils and chemically activate them, followed by a simple mixing procedure with hexylamine. It's a short-chain amine. What happens after simply mixing these chemicals together at a short time and neutral and relatively mild pH, we're able to coat the surface of the cellulose nanofibrils, as we can see in the picture, with amine chains that stick out radially from the surface. What this means is water, when it tries to touch the surface of the cellulose nanofibrils, is blocked by these amine chains. As a result, they repel water, and the contact angle of water increases dramatically. So what does this all mean for the resulting composite? My material can be dried using an oven, which is a pretty harsh drying method, chopped up and mixed with resin, and the resulting composite has a 40% increase in modulus and stiffness compared to the same quantity of the unmodified hydrophilic material. My research is the first step in applying natural material for high-performance composites, and it really does demonstrate that we can achieve high-performance composite materials without the requisite energy and by energy cost and using natural materials as the precursor. Thank you.